Hello guys, I hope you are all doing well and I hope your first major exam was a good one. So in this video I'll be solving all the 20 questions and that were on the exam, and I will be explaining how to solve them step by step. So and you'll find the questions in the description below, and there will be also, I will be adding the figures, so because we have figures in the exam. So it's not only the questions that will be in the description, but I will also be adding the figures. And I will be solving these questions in order, from 1 to 20. So let's get going. Let's start. Alright guys, so our first question here is a pretty straightforward question, and it's like a 3 minutes question. It's very easy. So in the question it says, we need to find the total heat energy, or the total energy per cycle. Like if you have a refrigerator and you want to figure out the energy per cycle, that is going to be equal to the QH, okay? So this is the quantity we're looking for and we're solving for. Okay, so we're given in the problem that the coefficient of performance of the refrigerator is 5. So K is equal to 5. Okay, so, and we're told that the compressor, so in a refrigerator, the compressor is the entity that does the work. The entity that does the work. So the compressor does 10 joules of work per cycle. Okay, so now we have a couple of values here. We have K, which is the coefficient of performance, which is given in the problem, and it is 5. And we have the work done by the compressor. Okay, so we have this equation now. 5 is equal to QL over 10. And we're asked to solve for QH. So this is pretty straightforward. We could use these two equations, equations 1 and 2. So just solve for QL. QL, if you multiply, for cross multiply, you're going to get 50. And if you plug your numbers into this equation, we know that the work is 10 joules. And we know that QL is, we just solved for it, it's 50. So if you take this to the other side, you'll be having 60. Okay, so QH is 60 joules, and it's the value we're looking for. It's the total energy used or exhausted per cycle in our refrigerator. Alright guys, so our second question here is a conceptual question, and it tests you on the idea of constructive and destructive interference between sound waves. So first off, we need to know that if the difference in paths, like, so we have a sound source here, and we have a sound source here, and we have a detector. Say it's a human here, okay? Say someone is standing there and is detecting the voices coming out of these sources, source 1, 2, 3, and 4. If the difference in paths between two sources is a multiple of lambda, so n here is an integer, okay? Integer. So if the difference in path between two sources is a multiple of lambda, then we're going to have constructive interference. The waves will add to each other and the voice will be louder. But if the difference in paths between two sources is a multiple of lambda plus 1/2 lambda, then we're going to have some sort of destructive interference. Okay, so that's aside. We can now analyze the figure in front of us and decide where we have destructive and where we have constructive interference. So the first thing to realize is that this distance here, so I call it C because it's from common. Let's call it the common distance. This distance is common between all the 4 sources. So all the 4 sources are going to be this distance away from the detector. This common distance plus, in the case of source 3, D, and in the case of source 2, it's 2D. And we know D is equal to lambda over 4. And in the case of source 1, we're going to have this common distance plus D plus D plus D, which is 3D. 3Ds. Okay, so let's write this down. Like source 4 is away from the detector C distance, and then source 3 is away from the detector C plus D, which is C plus lambda over 4. We're given the question that D is equal to lambda over 4. Okay, so and so on and so forth. So you just write this down, and you have this distance stated like this. And now all we need to do is actually test the choices. So in the choices, it says that the difference or the sources from source 1 and 3 are going to interfere constructively, which is not true. Like it's obviously destructive interference, because if you measure the difference in paths between 1 and 3, you just take this value, or actually you take this value and subtract it from this value, you're going to get 1/2 lambda. And we know if you have a multiple of 1/2 lambda, you're going to have destructive interference, and it says in the first choice it's constructive, so our first choice is out. And in the second choice, it says that the difference between, not the difference, it says the interference between source 2 and 4 is going to be constructive, and it's obviously not constructive, it's destructive. If you go ahead and subtract the path from source 4, which is C, if you subtract that from the path of source 2, which is C plus lambda over 2, you're going to get 1/2 lambda, and that's going to give you, as the rule says, destructive interference. So our second choice is out. So you can also cross the rest of the choices through this logic. And the last choice, which is choice E, I think. Yeah, choice E is the correct choice, because it says that the difference between source 1 and source 3 is gives you destructive interference. And that's it, that's your question. It's based on your understanding of wavelength. All right, so in our third question, we're going to use two equations. So we're given two engines, okay? A Carnot engine and a real engine. And we're given the temperatures of the hot part and the cold part of the engine. And it says in the question that the two engines, the Carnot engine and the real engine, have the same hot and cold parts temperatures. So our first step here is to convert units. So we're given the temperatures in Celsius, and we want to convert it into Kelvin. So if you want to convert Celsius to Kelvin, you just add 273. So if you add 273 to 500, you get this value, and 273 to 0, you get 273. All right, so it says in the problem that the efficiency of the real engine is 60% of the efficiency of the Carnot engine. So we don't know the efficiency of the Carnot engine, but we can calculate it from our equation sheet. So this equation is on our equation sheet, and it says if you subtract your ratio between the cold and hot temperatures from 1, you'll get the efficiency. So you go ahead and do that. So 1 is equal to 773 over 773, okay? So this is just another way to write 1. And then you take your cold temperature and put it in the numerator, and the hot temperature, and you put it, plug it into your denominator, and then you subtract these two values, and you get 0.65. So now we have calculated our efficiency of the Carnot engine. All right, so once we have that, we could multiply that by the value of this Carnot engine efficiency by 60 over 100. If you multiply this value by 60 over 100, you will get the efficiency of the real engine. Why do we get that? Because it says in the question that our efficiency of the real engine is just 60% of the efficiency of the Carnot engine. So now we have our two values. Once we get here, we can calculate the ratio. So in the question it says it's asking for the ratio between QH and QH of the real engine over the Carnot engine. So how can we get this ratio? Like, just from the efficiencies. Okay, so here comes the tricky part. it says in the question that the two engines does the same amount of work. So if we know that the two engines does the same amount of work, then we can use this equation. This is also straight out of your formula sheet. The efficiency of any engine is equal to the work done by the engine over the QH. So we know that this Q is the same for the two engines. So if you take the ratio between the efficiencies, so the efficiency of the real engine over the efficiency of the cold engine, the Carnot engine, and just replace this symbol by this equation or by this ratio. So we know that this symbol or the efficiency is equal to this, the work over the QH. So take this out and replace it by this, because these two are equivalent. Okay, so if you do that, we know that the work here is the same as the work here. It's clearly was stated in the problem. Because they're the same, they're going to cancel out, and we're going to have this expression. So now we know that if we divide our efficiency of the real engine by our efficiency of the Carnot engine, we're going to get the ratio between, or the ratio of the QH of the Carnot engine and the ratio and the QH of the real engine. Okay, just plug this into your calculator. Divide this value, which is 0.39, by this value, which is 0.65, and you will get this here. Once you get this, you're almost there. The question is asking for this ratio, the ratio of the QH of the real engine over the Carnot engine. But we have the Carnot over the real. So what do we do now? We just plug into your calculator 1 over whatever this number is, and you'll get your answer. And that is the ratio that we're looking for, and that's the answer for our question. All right, guys, so in question number 5, or actually question number 4, we're given a thermodynamic process. So the process goes from point 1 until it reaches point 2, and then from point 2 it reaches point 3. And we're asked to find the heat exchange that happens through this process. So we're going to kind of separate this problem to two parts. The first part from 1 to 2. Okay, so we know that the change in internal energy of any thermodynamic process is Q minus W. And we're interested in this here. The heat added or was taken from the system. So for the process from 2 to 3, so we're going to start by this process from 2 to 3. We know from the graph, from the shape of the graph, that there is no work done in this process from 2 to 3. Because there is no area under this line. Like if you have an XY plane and you have a vertical line like this, there is no area underneath this line, okay? But if you have an XY plane and you have a horizontal line like this, then the area under this line will be the work done in our thermodynamic process. Okay, so we cross this out. So our change in internal energy is going to be equal to the heat only. And we know that we can calculate this change in internal energy. We have a formula for that. Like it's the number of moles times the CV, or the specific heat, when the volume is constant, times the change in temperature. So change in internal energy, this formula is always true. Like no matter what thermodynamic process we have, like say it's a constant volume process, like here from 2 to 3 it's a constant volume process. So we can apply this formula, and here from 1 to 2, the volume is changing. Even though the volume is changing, we can still apply this formula, okay? So this is always valid. Okay, so the number of moles is given in the question is 0.1, and then CV we can calculate. We have requested that is monatomic gas. For any monatomic gas, CV is equal to 3 over 2 times R. R is 8.31, and you just multiply this using your calculator and you get this. So this is the value of CV, okay? So CV is 12.5, And now the change in temperature here, we don't have the temperatures. We're not given the temperatures. So we can use the ideal gas law, which is PV is equal to nRT, where P is the pressure, V is the volume, and N is the number of moles. R is our constant, and T is the temperature. So solve for the temperature, you get the temperature is equal to this. Okay, so from 2 to 3, we have two states, an initial state and a final state. So our temperature in the final state, so here is the final temperature minus the initial temperature, which is equal to the change in temperature, which is what you're interested in here in our equation. Okay, so our final temperature is equal to the temperature right here at 3. So what's the pressure and volume at 3? We just plug this into our calculator, the pressure at 3 and the volume at 0.3. And don't forget to use your conversion factors, because we're given pressure in atmosphere and atmospheric unit, and we want it in Pascal. This is the SI unit for pressure. So don't forget to use these factors, the conversion factors. And we're given the volume is centimeters cubed, and we want it in meters cubed. So 1 centimeter cubed is equal to 1 to the negative 6 meters cubed. Okay, so here is the pressure as 0.3 times the volume 0.3 over nr, and I already calculated nr to be this value. Number of moles times our constant. Okay, so here is the pressure and volume at 0.2. So it's the initial pressure and volume. So take this whole number and plug into your calculator, and you'll be getting this, negative 389. Just multiply everything and you'll get this value. And this value is equal to our heat exchange in the process from 2 to 3. So we have solved half of the question. We have solved this part. And now we're interested in solving this part, the heat exchange in the process from 1 to 2. So in the process from 1 to 2, unlike our the process from 2 to 3, we have some work. Because our line here, this line, is a horizontal line. So, and if we have a horizontal line, then we have an area. We have area under the line or under the curve. So how can we calculate the area? It's obviously a rectangle. So the area of a rectangle is basically the width times the height. So from here to here, it's the width is equal to 1. And from here to here, the height is equal to, sorry, it's not equal to 1. It's from here, from 800 to 1600. So here is equal to 800 centimeter cubed. And from the height from here to here is equal to, from 0 to 4, and that's going to be equal to 4 atmospheric units. Okay, so multiply this out and don't forget your conversion factors, and you'll be getting the work. So the work here is 800 times 4 times our conversion factors, and this is going to be equal to 323. So we have calculated the work underneath the horizontal line. So why are we interested in calculating the work? Because we need this value here, and if you take this value to the other side, we're going to have an equation like this. We're going to have the change in internal energy plus the work done is equal to the heat exchange in the process from 1 to 2, and we're solving for it. So we already done this. It's equal to 323. And now we're interested in this here, the change in internal energy. We use our same old formula, this formula. Number of moles times CV. This is number of moles, this is CV. And times the change in temperature. And we calculate the change in temperature by the same old method, which is stated here. And then if you plug this here into your calculator, you're getting 389, and if you multiply everything out, you're getting 486. And just add the work to the change in internal energy, and you'll be getting this value here. This is the heat exchange from in process 1 to 2. Alright, so now we have done this. We found this, and we found this. Okay, just add this number to this number, and you'll be getting 323 joules, and that's your answer. Alright guys, so question number 5 is a pretty quick question. So we have 2 rods. This rod is made out of steel, and this rod is made out of brass. These rods are separated by 5 times 10 to the negative 3 meters. It's basically 5 millimeters, but we multiply it by 10 to the negative 3 to convert it to our SI unit, which is meter. So we apply some sort of heat. We heat this up, okay? We heat both the rod, both the brass and the steel rod up. And we're asked to find the final temperature at which the two rods meet. So we know from our thermodynamics lessons that when we heat something up, it expands, its length increases. And the equation for expansion is going to be equal to the change in length. This is the change in length. The coefficient of expansion times the initial length times the change in temperature, okay? If you expand this, you're going to have T final minus T initial. Okay, so we want the increase in length of steel plus the increase of the length of brass to be equal to the gap between them. Because we're interested at the temperature when the two rods meet, when the gap between them is equal to 0, okay? 0 meters. So we're interested in the final temperature when the expansion of the steel is plus the expansion of the brass is equal to 5 millimeters. If you write the equation for this, which is there, the coefficient of expansion for steel times the length of steel. So one thing I didn't say, that the length of this is 1 meter and the length of this is also 1 meter. So this makes our calculation way simpler. This cancels because it's 1. And if you plug your numbers in, the initial temperature is 25 Celsius degrees. It's given in the problem that the initial temperature is 25. So the initial here is 25, and we're interested in solving for the final temperature. So we know the coefficients of expansion of brass, which is this, and the coefficient of expansion of steel, which is 13 times 10 to the negative 6. It's given in the problem. And our net expansion should be equal to this value. Now all you need to do is actually plug this equation into your calculator and solve for T final. It may take a couple of seconds, but it will do all the algebra for you. And this is your answer. This is going to be 181 Celsius degrees. And that's it. All right, guys. So question number 6 tests you on the second law of thermodynamics and tests you on your understanding of this equation. The equation of change in entropy, which is equal to the integral of QD over T, where Q is the heat and T is the temperature. Alright, so for Carnot engines, we know that there is a condition for Carnot engines that QH over Q or TH is equal to QL over TL. This is true for all Carnot engines. And we know that change in entropy for a Carnot engine is divided into 2 parts. The first part, change in entropy in the hot reservoir, and change in entropy in the cold reservoir. Okay, so using this equation, that we could rewrite the change in entropy as QH over TH, and here QL over TL. And we know this value and this value are the same. So if you subtract them from each other, you get 0. So change in entropy for all Carnot engine is 0. Alright, so now let's go to the real engine example. So the second law of thermodynamics says that for any reversible thermodynamic process, our change in entropy is equal to 0. But for any irreversible thermodynamic process, the change of entropy must be positive. It cannot be negative. So it's either 0 or positive. So the statement of the second law of thermodynamics can be like rephrased as change in entropy can never be negative. It can be either positive in the case of irreversible thermodynamic processes, and it can be 0 in the case of reversible thermodynamic processes. So we know by definition that real engines are irreversible processes. irreversible thermodynamic processes. So, and we know that from the second law of thermodynamics that any irreversible process, in any irreversible process, the change in entropy must be positive. So our last case is here is the perfect engine. Okay, so in a perfect engine, we have a hot reservoir and we have a cold reservoir. And we're assuming that we're extracting heat from the cold reservoir to the hot reservoir without doing any work. This is the definition of a perfect engine or a perfect refrigerator. Okay, so this yields that QL is equal to QH. So QH is equal to QL in a perfect engine. So if this is the case, then these Q's are going to be the same. And we know that the hot temperature is bigger than the low temperature. So if we divide Q by a very large value, we're going to get a small number. So this whole number is going to be small. And if we divide Q by the same Q by a small value, the low temperature, so we're going to have a bigger value. So our change in entropy is going to be negative. And this is not permissible according to the second law of thermodynamics. And that's the question. If you understand this, the second law of thermodynamics and change in entropy of entropy equation, you pretty much solve the question. Okay, guys. So for problem number 7, we're given 3 things. We're given the volume of some gas, and we're given the pressure, and we're given the average kinetic energy of the molecules of the gas. And we're given that the gas is ideal. So and we're asked to find the number of moles of the gas. So first things first. So we know the average kinetic energy, and we know this constant. This is the constant, and we know this equation, okay? This is the equation for average kinetic energy. So we could just solve for temperature here. If you divide both sides by K and multiply both sides by 2/3, you'll get the temperature. So just plug your values in, 2/3 times K. K is in your equation sheet, and the average kinetic energy is given over here. And if you plug this into your calculator, you'll get this temperature. So now we can utilize our ideal gas equations. So we know that this is the number of mole here, moles. Just divide both sides by RC, and you'll get the volume multiplied by the pressure over the constant R times the temperature is equal to the number of moles. So, and we have the pressure, we have the volume, we have the temperature, just solve for it, and R is the constant. Plug your numbers into your calculators, and you will be getting the number of moles. Now, keep in mind that our SI unit for volume is meters, and it's given in centimeters, centimeters cubed. So in order to kind of convert it to meters cubed, you have to multiply by 10 to the -6. And if you plug your numbers into your calculators, you'll be getting this. So question number 8 is a rather long and very involved question. So I've decided to sort of divide it into 5 parts. Okay, so in the statement of the question, we're given that we have a diatomic gas, which means we have two atoms. For example, we have oxygen. So oxygen is like something like this. So we have 2 atoms connected to each other. And the second thing, we're given the number of moles, and we're given the initial temperature. We're given the initial and final pressures, and we're given that the process, or the thermodynamic process, is adiabatic. So what does it mean to have an adiabatic process? It means that there is no heat exchange in the process, or heat is equal to 0. So our change in internal energy equation reduces to this, because we cancel this out. Okay, so step by step we cancel the question. So the specific heat, when the volume is constant, is for any diatomic gas, is given by this, 5/2 times R, and if you plug your values in, you get this number. And we will also need the specific heat when the pressure is constant. So just add R to our value, and we get this. Alright, so gamma is also a constant that we're going to use in this question, and it's equal to Cp over Cv, and that's equal to 1.4. Alright, so the first step to solve this question is to calculate the initial volume, which is not given. We can utilize our ideal gas equation and isolate V1, and then plug your values in. Number of moles is given in the question, which is 0.5. R is just constant. This one is 273, which is given in the question. Over the initial pressure. The initial pressure here is given in atmospheric units. So we just multiply it by 1 times 10 to the power 5. So now we have calculated the initial volume. We can calculate the final volume using this equation. This equation is only for adiabatic processes, and it's given in your equation sheet. Okay, so just solve for V final, just a little bit of algebra, and you'll be getting this expression. Gamma is, we already solved for it, it's 1.4. And we know the initial final pressures and the initial volume, which was solved for in here. And if you plug your numbers into your calculator, you will be getting this volume. Alright, so the third step, this is the third step, is calculate the final temperature. We again use the ideal gas equations, and we solve for T final, and we're getting 640. Once we do that, we could use the equation for change in internal energy for any gas. This equation holds for any thermodynamic process. And if you plug your values in, like we have the number of moles and we have CV, we calculated right here. We have initial final temperatures, and just plug your values in into your calculator, and you'll be getting this number. And this is the amount of the work that we have done compressing the gas. Alright, that's it, that's your answer. Alright guys, so in question number 9, we're asked to find the ratio between the fundamental frequency of sound in a fluid over the fundamental frequency of sound in air. So we're given that the speed of sound in air is 343, and in a fluid, in an unknown fluid, we're given that the speed of sound in that fluid is 1,482. Alright, so in order to kind of find the ratio between the two fundamental frequencies, we need to know the equations. First, our equation for the fundamental frequency of sound in air is going to be this equation. And it's straight out of your formula sheet. Why? Because when you have a tube and the tube is open at both ends, we use this equation. Okay, so the question says that we close the tube from one end and fill it with some sort of fluid. So in order to find the fundamental frequency of sound when the tube is closed, we just change this 2 into 4. So and now we just plug our values in. We're given in the question that L is 1, so this is going to cancel. This L and this L will cancel. And we know that we're dealing with fundamental frequency. Fundamental frequency means first frequency. So N must be 1 here. If N is 1, then our equation reduces to this. So these are our two equations for fundamental frequencies. Now all we need to do is actually find the ratio. This is in a fluid, the fundamental frequency in a fluid, and this is the fundamental frequency in air. Okay, so take this and put it here, and take the other one and put it right here. Because it says in the question that we need to find the fundamental frequency of sound in fluid and then over in air. Okay, so we just plug our speeds in as given in the question. And when we have a sort of large line, then it means that we need to do the small lines first. So divide this number by this number, and you'll get some sort of answer in your calculator. And divide this answer by 343 over 2, and you'll be getting 2.16. And that is going to be your answer. Alright guys, so question number 10 is a pretty straightforward question. And it says we have some grams of ice, and we took some water at 30 degrees Celsius, and we pour, actually we have 150 times 10 to the negative 3 kilograms of ice, of water, and we poured this amount of water on the ice. And we're asked to find how many grams of ice or how many kilograms of ice are going to melt if we do that, if we pour the water. So let's first assume that the equilibrium temperature between ice and water is going to be 0 degrees. And based on that assumption, we can solve the question. So in order to calculate the amount of energy that's going to we take from water in order to turn it to 0 Celsius degree, we use this equation. The amount of energy is equal to the mass times the specific heat of water or times the change in temperature. So if you take water from 30 to 0, the change in temperature is going to be negative 30. And this here is out of your formula sheet, the specific heat of water in joules. And this is the given mass of water. Multiply things out and you'll be getting this amount of energy. Okay, so it says in the problem that the ice is at negative 5 degrees Celsius. So we want to know the amount of energy that takes to change the temperature of ice to 0 degrees Celsius. All right, so same thing here. So amount of ice times the specific heat of ice, and multiply that by the change in temperature. Like if you take ice from negative 5 to 0, you'll be changing temperature by an amount of 5 Celsius or degrees Celsius. Just multiply things out, so I'll be getting this number. Okay, so we're going to water is going to provide this amount of energy to melt the ice. But the ice does not melt at negative 5, it melts at 0. So we're going to take this amount of energy and subtract it from this amount of energy in order to know the melting energy. Melting. Okay, so if you actually, yeah, so you subtract these two values, and you'll be having something like this. This energy is the energy that is going to be used when ice is at 0 degrees Celsius. And it's the energy that actually melts the ice, because we know ice does not melt at negative 5. All right, so take this energy, and we know that the latent heat of fusion times the mass of the ice gives you the amount of energy we need to melt some amount of ice. Like if you divide this equation by the latent heat of fusion, and you isolate the mass, and you're given a specific amount of joules here, then we could figure out the amount of kilograms that can be melted by this amount of energy. So now just here, plug your numbers in, you have this number, plug it in here, and the latent heat of fusion is given in the question, and divide them, and you'll be getting this answer, and this is the right answer. All right, so as far as question number 11 goes, there exists two ways to solve the question. One is the long way. So the question is asking about the transverse speed. So the transverse speed is basically the speed of the particles that are going up and down, and the transverse speed is the speed in the vertical axis. Like we're not talking about the wave speed in the horizontal axis, we're talking about the particle speed up and down. One way to solve the question is to use the wave equation, and we take the derivative for this equation, and the derivative for the wave equation will be giving you the wave speed. And that's a very time-consuming way, but there's a very, very quick way to solve this question. Okay, so it's given in the problem that the wave is moving to the left. So imagine the blank wave is moving to the left. Then I drew using the green dotted line. So the green wave is basically the wave after 1 second. Okay? So it's moving to the left. We know that. We know this. So we're going to solve the question using the sign of the velocity. And this solution right here uses the numbers and the sign, but you could solve it solely by the signs. Okay, so at point 3, the transverse speed of this particle must be negative because it must move downward. Like if you kind of shift the wave to the left, because it's moving to the left, then you know the position, this position of the particle 3, in order for the wave to sort of move to the left, the particle must move to this position. Otherwise, if the velocity is positive, if the particle goes like this, then the wave will not be moving to the left, the wave will be moving to the right. And by the same logic, particle 1 must have positive velocity because it's moving upward, and in order to make the wave move to the left, in order to fill the gap right here, so in order for the wave to move to the left, particle 1 must move up to this part, so the wave is moving to the left, and if particle 1 does not move up, we're gonna have a gap in the wave, and this cannot be. Okay, so if you know the sign of particle 1 is going up, so it's positive, and this sign is negative, and the velocity, so from our understanding of transverse waves, we know that the velocity at the peak is always equal to 0. Because what's going on is basically some sort of acceleration, some sort of downward acceleration. So the particle is going upward with a positive velocity, and the downward acceleration is basically decreasing the velocity until it reaches this peak. And once it reaches this peak, it will be 0. The velocity will be 0, and the particle will start accelerating, actually moving with a negative velocity in a simple harmonic way, as we explained in the chapter 16 video. So if you know that particle 1 has a positive velocity, and particle 2 has 0 velocity, this is 1, and this is 2. And particle 3 has negative velocity. You could clearly see that choice B is the answer, or actually choice A is the answer. I didn't explain it the long way because it's very time consuming and I'm kind of running out of time. So yeah, that's your answer, choice A. Alright guys, so question number 12 asked us to find the maximum power. So in the choices we're given some sort of variables, and these variables are multiplied by factors of 2 or divided by factors of 2. So the first thing that we need to do is write down our power equation for transverse waves, which is this equation. So these two, 1/2 mu is constant, are constants, and they're not involved in our question, so we're going to ignore them, okay? So we only care about this part. Okay, for this part, in the choices, we're not given omega, okay? We're given the frequency. And we know that omega is equal to 2 pi the frequency. Okay, so we could rewrite this equation as this equation. Okay, and in the choices, the amplitude is written as A rather than Ym. So our final equation that we're going to work with is going to be this equation. Alright, so the first choice, it says we have a speed of 2v and we have a frequency of f/2. So if you plug these values, if you plug it in this equation, we're going to get 1/2 of the power as if we had the variable as v, a, f, without any factors of 1/2 or factors of 2. So here is equal to p, okay? But if we add these factors, we're going to have 1/2 the power. And the same thing goes for choice B. If you plug these variables in here, you'll also be getting 1/2 of p. P is this. Okay, so p is equal to this. Let's write it explicitly. Actually, yeah, it's already written right here. This is P. And choice C is our right answer because it gives you 2p of power. It multiplies our power by 2, a factor of 2. And the last two choices is going to give you the same thing as if you didn't add any factors. Actually, this here is equal to p because we didn't add any factors. And this here, these two factors cancels out if you plug it into the equation. So our choice C is the maximum magnitude of power because it multiplies our power by factor 2. Guys, so in question number 13, we're asked to find the work done, which is the area under this curve, in an isothermal process. So we don't know the area under this curve, so we can't use this method. And we know that if the process is isothermal, the temperature is going to be the same, 85 Celsius degrees or 358 Kelvin. And in this condition, under this condition, if the temperature is constant, we call the process isothermal and we use this equation to find the work. So before we use this equation, we need to figure out the number of moles and we need to figure out the initial volume. We're given the final volume, which is here, 0.100 meter cubed. And once we figure out the number of moles and the initial volume, we could just plug our numbers in and we figure the work out. Okay, first let's find the initial volume. So we know that from our ideal gas equations that PV is equal to nRT. But T here is constant. So if T is constant, then the initial pressure and the initial volume is going to be equal to the final pressure and the final volume. So using this equation, we could just solve for the initial volume if we divide both sides by P1. And if we plug our numbers in, we're going to have 1/30 meters cubed. And you need to pay attention that the unit here is atmospheric pressure. So just multiply by 1.01 times 10 to the 5th. And before you plug in your numbers into your equation. So once we figure out the first volume or the initial volume here, so we know that the volume here is 1 by 30. Now it's time to figure out the number of moles, or N. We again utilize our ideal gas equation and solve for N, and then plug any pressure or any volume over RT. I use the initial pressure and initial volume here, and I get this number of moles. And once I get this number of moles, the rest is just plugging numbers into your equation. This is coming out of straight out of your equation sheet, and like N here, which is the number of moles, and like the initial volume and the final volumes, and you'll be getting this number, and that's the answer. It's your answer. All right, guys. So question number 14, we're given the molar mass and the temperature. So we're given various molar masses and various temperatures, and we're asked to compare the RMS speed. So the RMS speed has an equation that is what was derived in class, okay? But it's written in your equation sheet. Okay, so we care about the temperature and the molar mass. So we cannot take this out, the square root of R over, okay, so this must be square root of R. So, and times the square root of R times the square root of Z, where Z is the temperature over the mass. Okay, so we only care about Z, okay? Z is the temperature over the mass, and it's the value that if it's big, then our RMS speed will be big. All right, so we're given here various temperatures and various molar masses, and if you plug the numbers from your choices to your Z, then you'll be having sort of a list like this, and a little bit of math here, and you will see that choice C is the biggest number out of all these numbers. So choice C must be your answer, and it must be the highest RMS speed. Alright guys, so question number 15 is about Kepler's equation. Okay, so in this question we said there is an observer which has zero velocity, so it's a stationary observer, and we have two sound sources. Okay, say we have some sort of sound source in here, let's call it B, and we have a sound source called A. So B is moving towards the observer, and A is moving away from the observer, and these two sound sources have a speed of half of the speed of sound in air. The speed of sound in air is 343 meters per second, so half of that is 171.5. They both have the same velocity, and they both emit the same frequency. Okay, so, and we're asked to find the ratio between the frequency that the observer hears from B over the frequency that the observer hears from A. So we know that the observer does not hear the actual frequency from these two sources because these two sources are moving. They have some sort of velocity. So we need to find the ratio of the frequency of B over the frequency of A as heard by the observer. Okay, so let's apply our Kepler equation. Kepler equation says that if we have a moving sort of source, then we multiply the original frequency times, as we can see from this equation, the speed of sound, plus or minus the speed of the detector. The detector here is not moving, it's, so 0, over the speed of sound, plus or minus the speed of the source. So, if the source is moving towards the detector, then the sign here must be negative. Why? Because we want to make the denominator small, because it's moving towards the detector. So if the denominator is small, our f prime is going to be bigger. Okay, so that's how we set up our first equation. Our second equation is basically the same way, except for the sign. Okay, so on the numerator we have the speed of sound, and the speed of the detector is 0. On the denominator we have the speed of sound plus the speed of the source. So here the source is moving away from the detector, as you can see. So since the source is moving away from the detector, we're trying to make f prime smaller than f original prime. So f prime must be smaller than f. How can we make this number small? We try to make the denominator bigger. And we only can do that if we add a plus sign here. If you add a negative sign here, then that's going to sort of make it smaller. Okay, once we calculate this through our calculators, we will see that the fb prime is equal to fb times 2. And if a prime is equal to fa times 2 over 3. And if you divide both of these numbers, like fb over fa, we know that fb is equal to fa, so this is going to cancel. And we're going to have something like this, 2 over 3, and that is equal to 2 times 3 over 2. 2 is cancelled, and our ratio will be 3, and that's your answer. Alright guys, so for question number 16, we're given a sound level of 70 decibels, and we're told that the intensity of the sound was decreased by a factor of 20. So when we say that something was decreased by a factor of 20, it means that we divided that thing by 20. If somebody tells you we're going to decrease the temperature by a factor of 2, it means we will divide it by 2. And if he says we will increase the temperature by a factor of 100, it means we will multiply it by a factor by 100. Okay, so we'll decrease the intensity by a factor of 20, and we're asked to find the sound level after we decrease the intensity by a factor of 20. Okay, so we're given the sound level, the initial sound level. We have this equation that relates sound level with intensity. So we plug our number here, and we could solve for I, or the intensity, that corresponds to this sum level. A little bit of math, and you will find that your intensity is equal to 10 to the power of -5. Divide that by 20, and you'll be getting 5 times 10 to the -7. And then use this equation again with the new intensity that was decreased by a factor of 20. Like here, your new intensity, which is 10 to the -7, over I naught, which is a given number, a constant number, times log 10 times 10. And you'll be getting the new sound level. And that's your answer. Pretty straightforward. Question number 17 says that we have a standing wave, and the harmonic is the third harmonic. So a string with a standing wave doing a third harmonic. If we have n to be equal to 3, then we have 3 half circles. And the length of our string is going to be lambda plus 1 half lambda. This is 1 lambda, and this here is 1 half of lambda. Okay guys, so the only way that I could solve this question is by thinking of this wave as a regular transverse wave. So I used the transverse wave equation, and I said that the value of sine must be equal to 1/2 in order to have a displacement of 1/2 the maximum amplitude. So in the question it says that at 30 centimeters, the amplitude is half of the maximum amplitude. Half of the maximum amplitude, the only way we could get this value to be half of the maximum amplitude is by having the sine here, the sine, to be equal to 1/2. And this is equal to 1/2, sine is equal to 1/2 when our angle is 30 degrees. So we could use this relationship right here that says that the angle over 360 is equal to the length over lambda. So when the angle is 30, the length, when the angle is 30 degrees, the displacement is 30 centimeters, or 30 times 10 to the -2 meters. So if we solve for lambda, we get lambda to be equal to 3.6. And we already know that the length of the string is equal to 1 lambda plus 1/2 of lambda, because we know that we are in the third harmonic, as given in the question. So if lambda is this value, then we just add 3.6 plus 1/2, 3.6, and that is going to be equal to 5.4, and that shows A. And hopefully this is the right answer. I'm not really sure about it. I'll be asking my professor as soon as possible, and I will update the video in case this is not the wrong answer. This is not the right answer. All right, guys. So question number 18, we're given this figure, and we said we have some sort of thermodynamic process going from I to A, and going from F to I. So this is process A, and this is process B, okay? So, and we're asked to compare between the value of the heat of B and the value of the heat of A, heat exchange or heat change. So we know from the graph that the work done by process B is smaller than the work done by process A, because the work done by A is equal to blue plus green area. Okay, so blue and green, because the work done is by definition the area of the curve of the PV graphs. But the work done by B is only the green area. So if we know that work B is bigger than work A, and we know that change in internal energy, this is the first law of thermodynamics. Okay, so by the first law of thermodynamics, we know that change in internal energy is equal to Q minus W. Okay, so from I to F, this is that change in internal energy, okay? From I to F, or for process A. And here is the change in internal energy for process B. And we know that if we start from the same point and we travel along the graph and then we return to the same point, then our change in internal energy must be zero. So change in internal energy happened in process A plus the change in internal energy happened in process B must be equal to zero. So if that's the case, then this value right here, must be equal to the value right here. The change in internal energy in both processes must be equal. Okay? So if we know that, and we know that the work done by A, or the work in the process A, is bigger than the work in process B, then this necessarily and logically means that QA is bigger than QB. Because this here is bigger than this, and these two are equal, so this QA must be bigger than QB. And that's your answer, that's the answer for the question. Our last, second to last question, over here, question number 19. It says that we have two strings. So one string has a linear mass density of 100 gram per meter, and the other string, string number 2, has a linear mass density of 6 times the first one, or the first string. And we send some sort of transverse wave through this string, and we know that the tension is 5 newtons. It's constant throughout the whole string. And we're asked how much time it takes for the wave to travel from here, from point A to point B. So we need to divide the problem into two separate parts, okay? The first part is, deals with the first string. Okay, so the velocity of the wave in the first string is equal to the tension over the linear mass density, which is 5 times the square root of 2. Okay, so and the velocity in the second string is equal to this 5, the square root of 5 over the 6 times the first linear mass density, and it's going to be equal to this number. So now we have the two velocities, and we know that the distance between here and here is 1.5. So if we divide distance by velocity, we get the time. So this here is the time 1, and here is time 2. And if you add time 1 and time 2, you'll be getting 0.73, and that will be your answer. Alright guys, so our last problem here, problem number 20, is a pretty fun problem, and it's a problem about tea. For tea lovers, you're going to enjoy this problem. Okay, so we have a pot of tea, and we have some sort of fire here, and we're trying to figure out the temperature of the fire. Okay? So we're given some information about the tea and the pot. So it says in the question that the temperature of the water is 100 degrees Celsius, and we know the cross-sectional area of the pot, and we know the thickness of the base of the pot, and we know that this amount of water, which is 0.39 kilograms, evaporates each 3 minutes. Okay, so what does this mean? We know that the energy that takes to evaporate a specific mass of water is equal to the latent heat of evaporization of water times the mass, and we get the energy. So we have the mass, and we know the latent heat of evaporization, and we could multiply these together and divide that by 3 times 3 minutes, equivalent to seconds. So 3 times 60, if you divide this energy by 3 minutes, then you're going to get the amount of energy that we exert on the water each second, or the power. Okay? So once we get the power, we could use this equation. This equation gives you the power also. if you have a hot and a cold kind of object, and we know the length between the hot and the cold object, and the length is given here to be 8.5 millimeters, and you just convert it to meters. So we know the length between the hot and the cold object, and we know the temperature of the cold object. The water is relatively cold, so it seems like 100 degrees Celsius is hot to us as a human being, but relatively it's colder than the fire. So here the temperature of the cold object is 100 degrees Celsius, and the temperature of the hot object is the quantity we're trying to solve for. So A here is the cross-sectional area of the base of the pot, and K is the thermal conductivity of the material of the base. And everything here is given except the power, which we solve for. So if everything is given and everything is known except for this value, we just solve for it here, and then plug your numbers in, and you'll be figuring out that the temperature of the fire is 105 Celsius degrees, or degrees Celsius. And that will be your answer. Okay, so that's the end of our video, and these are all the problems in the major. So I hope you guys enjoyed the video, and I hope this video was useful to you. Feel free to comment down below if you have any questions on physics or in the major. I will put my email down there in the description, so just email me if you have any questions. Also, do let me know if you have any comments or suggestions about my videos. I will be very happy to read your comments. And thank you.